Hi everyone, just addressing your feedback as usual. Let's see here. Does an orbital have a certain ionization energy which determines a jump in ionization energies? Yeah, to a certain extent they do. The orbitals will, yes, the orbitals themselves have their own energies, and the ionization energy is how much it takes to pull an electron out of that orbital. So if you look at the filling order, the energy level diagram for the orbitals. So we would have, I'm going to do boron here. So boron has 2 electrons in a 1s orbital, and then it has 2 electrons in a 2s orbital, and then it has 1 electron in its 2p orbitals. To ionize it, you need to raise its energy. You need to pull it away from the nucleus. So if you want, again, I kind of like thinking about my energy level diagrams like this. You can make a correspondence between the positions, the difference in space between these electrons and the nucleus. You can make a correspondence between that and the energy. As you raise them away from the electron, their energy increases. It goes negative to positive. So anyway, the point being that to ionize something means to raise it infinitely far away from the nucleus. So you would want to take this electron and pull it all the way up here. So the 2p orbitals have higher energy than the, say, the 1s orbitals. So these electrons, you need to provide even more energy to remove them. So there is a bit of a correspondence between the actual energy of the orbitals and the ionization energy of an electron from one of those orbitals. Normally we do, when I generically say ionization energy of an element, it's normally implying that you're talking about the first ionization energy, and specifically that you're talking about the energy required to remove the electron from the highest energy orbital. This is the one that's going to be the easiest one to remove. But there's nothing that says you can't take out a 1s electron from a beryllium atom. That's perfectly allowable. So there's experimental techniques that actually work solely on that principle of taking out the core electrons but leaving the valence electrons intact. And it's much harder to remove the core electrons. They're much closer to the nucleus. They're buried down deep towards the nucleus. They're held on by strong electrostatic forces, and they're lower in energy. So it takes more energy to raise them out of the potential well. Could you repeat the exceptions and explicitly write the 3 trends? I will discuss the exceptions, but I'm going to focus first on the 3 trends here. So people wanted the explicit trends. So here are the different properties whose trends you should memorize. Atomic radius. Generally, I'm going to write all of my arrows showing an increase. So generally, atomic radius increases as you go left on the periodic table, and it increases as you go down on the periodic table. So the smallest element is helium, and the largest element is cesium. So there's a general trend as you go from the top right corner to the bottom left corner. That's the trend for atomic radius. Other properties you should know: ionization energy. That generally increases as you go across the periodic table, and it increases as you go up in the periodic table. So the element with the highest ionization energy is helium. The one with the lowest ionization energy is cesium. And I think that addresses another question that somebody had: which element has the highest ionization energy or the highest effective nuclear charge? That's going to be helium. Helium has the highest ionization energy, or the highest first ionization energy, I should say. And I'll give you a couple of other trends here. Electron affinity. I didn't explicitly discuss electron affinity. Partly because it's not as useful of a concept as ionization energy, but electron affinity is essentially ionization energy in reverse, kind of. Electron affinity is the energy that is released, or the energy change for gaining an electron. Ionization energy is how much energy you need to pay to remove an electron. Electron affinity is how much energy you get back when you stick on an electron. So it's the opposite process, and they generally follow the exact opposite trend. So I'll tell you that electron affinity, so that's electron affinity, tends to increase as you go across the periodic table, and it actually increases as you go up in the periodic table. So it follows a slightly different trend than ionization energy. But yeah. And then effective nuclear charge, the last one I'll give you guys, effective nuclear charge. Where do I want to put this? I guess I'll put this over here with atomic radius. Effective nuclear charge increases as you go across the periodic table, and it also increases as you go down the periodic table. So that seems to be a little bit counterintuitive for some of these trends. Okay, it makes sense that effective nuclear charge should mirror atomic radius. As your effective nuclear charge increases, your electrons are being pulled towards the nucleus more tightly, so the element shrinks. The effective nuclear charge increases as you go down the periodic table, so you would expect then that, okay, then the atomic radii should decrease. The counter argument to that is that as you go down the periodic table, you're putting electrons into larger orbitals. Like the actual orbitals themselves get larger and larger as you go up to higher principal quantum number. So there's multiple effects to take into account to explain the trends. Or there's two effects to explain the trends, or to argue about why the trends are what they are. One is on the basis of effective nuclear charge, and the second is on the just foundationally the size of the orbitals themselves and their standard energies based upon quantum mechanics and understanding of the filling orders of the electrons. The exceptions, I'll talk about the exceptions in just a second. Can you go over the difference in the ionization energies? I don't understand the difference between the large jumps in successive ionization energies and the fact that the ionization energies increase. So let me discuss that. So here is the general trend, that as you strip more and more electrons off of the atom, it gets harder and harder to strip more electrons off of the atom. So the ionization energy, the second ionization energy of an element is always larger than its first ionization energy. And similarly, the ionization energy of the third electron that you pull off is always going to be greater than the energy required to remove the second electron. So it just gets harder and harder as you remove electrons. So that's just the general trend. Ionization energy should always increase successively. But there are some jumps that we can talk about. So I'll do lithium and beryllium. So lithium's ionization energies follow this pattern. Beryllium's ionization energies follow the same pattern. They also increase. And then beryllium has a fourth ionization energy. Lithium only has three because it only has three electrons. So they both follow the same trend. The difference between them is where the jumps occur. For lithium, there is a big jump. So I'll say not just greater than, but much greater than. The second ionization energy is much, much larger than the first ionization energy for lithium. For beryllium, that jump occurs between the second and the third ionization energy. So there's a big jump between the first and the second for lithium, big jump between the second and the third for beryllium. And the way we explain that is by looking at the orbitals that you're taking electrons out of. For lithium, its first ionization energy, you're taking it out of, well, what is lithium's electron configuration? It's 1s, 2, 2s, 1. So for that first electron, you're taking it out of the 2s orbital. For the second ionization energy, you're taking it out of the 1s orbital after you've stripped away the the electron from the 2s orbital. After you've stripped that away, any other electrons are going to come out of the core orbitals. And similarly, for the third ionization energy, you're also taking that out of the 1s orbital. For beryllium, this jump occurs later because beryllium's electron configuration is 1s2, 2s2. So you start by taking an electron out of the 2s orbital, then you take an electron, your second electron, you also take out of the 2s orbital. By the time you get down to the third ionization energy, you've stripped away all the 2s orbitals, and now you're taking an electron out of a core orbital, out of the 1s2, out of the 1s orbitals. And then the last one here, you're taking it also out of the 1s1. So the large jumps, they all should increase, but the large jumps occur because of the electron configurations of the elements, which orbitals you're taking them out of. And as you go across the periodic table, you have more electrons in the valence shell that you can take electrons out of before you run out of valence electrons, and all of a sudden you start taking electrons from the core. So that, I hope, clarifies the difference between those general trends. So another follow-up question here was, can you go over the difference in the ionization energies? Is it related to the number of electrons in an atom? It's not related to the number of it is related to the number of electrons in the atom, but more importantly, it's related to the orbital that you're taking the electrons out of. That's really the key determining factor. The orbitals that you're taking electrons out of depends on the number of electrons because there's a basic filling order that's always going to be followed. But the real connection between ionization energy, successive ionization energies, and electron counts is the orbitals that you're taking electrons out of. So that's the real difference. Can you go over how atomic radii, effective energy, electronegativity, and ionization energy, how are they all proportional? Okay, so the general proportionalities here. So I'll give you guys the general proportionalities here, or the most important ones. Ionization energy. Well, let's start with Coulomb's law here. Coulomb's law tells us that the energy, the electronic energy that an electron experiences is inversely proportional to its the charge on one of the species, which in this case is the nucleus, which we'll represent with an effective nuclear charge, and it depends on the distance between the two of them. So I've been talking about forces for Coulomb's law, but forces are also related to energy, so they follow a similar but slightly different functional form, because it goes as r squared as opposed to r. So generally speaking, the energy should be proportional to the effective nuclear charge. So you can say that ionization energy is proportional to effective nuclear charge. And I've erased the trend already, I apologize, but yeah, as you go across the periodic table, the effective nuclear charge increases, and so does the ionization energy. You can say also that the atomic radius, I'll just say radius here, that should be inversely proportional to the effective nuclear charge. And I admit that doesn't seem to quite follow this, but bear with me. As the effective nuclear charge increases, electrons are being pulled more tightly towards the nucleus. So there should be a general trend that as your nuclear charge increases, yeah, you're holding on to your electrons more. So as this goes up, the radius should go down. So they have an inverse relationship. And then similarly, you can show that ionization energy is inversely proportional to the radius. And that follows fairly nicely from this relationship. As you start with your, again, there is a correspondence here between energy and the radius. As your radius increases, your energy goes up and up. It's becoming less negative. These all have, technically, this point here being completely ionized, that would correspond to 0 energy, and then this guy down here has a relative negative energy. So as you increase the radius, your energy goes up and up. So you can say that, okay, as ionization energy, why is that inversely proportional to the radius? Is that if you're starting with your electrons further away, your relative energies are going to be higher. If you want to ionize it, you need to spend less energy to pull it up away from the nucleus. So those are all inversely proportional. Okay, the exceptions. There are 2 big exceptions, which are as you go from the S block to the P block. So there are 2 big exceptions for ionization energy that people should be aware of. These are the exceptions. So as you go across the periodic table, generally ionization energy increases, except when you go from beryllium to boron. Boron actually has a lower first ionization energy. How do we explain that? So beryllium, it's based upon their orbital structure and the relative energies of the orbital. So beryllium has an electron configuration of 1s2, 2s2, 2p, no, just 2s2. And then boron has an ionization energy of, has an electron configuration of 1s2, 2s2, 2p1. So ionization energy, it's how much energy you need to spend to lift the electron out of its orbital, pull it off of the nucleus. So normally, yeah, we would say that ionization energy, we would predict it should increase because you assume that your effective nuclear charge is increasing, going from beryllium to boron. Except that boron, when you pull off its electron, you're pulling it off of a 2p orbital, as opposed to in beryllium when you're pulling it off of a 2s orbital. And generally speaking, the 2p orbitals are higher energy than the 2s orbitals. So it's a little bit easier to lift an electron out of a 2p orbital. You have to spend a little bit less energy than if you try pulling an electron out of the 2s orbitals. Here, that energy difference is greater for a 2s orbital than for a 2p orbital. So you don't need to spend as much energy. So beryllium's ionization energy is a little bit less than, no, boron's ionization energy is a little bit less than the ionization energy of boron versus beryllium. So that's one exception that we explain based on just the relative energies of the orbitals that you're pulling electrons out of. Again, so the previous question was, do the orbitals themselves have energies that determines their ionization energy? Yes, they do. This is a great example of that. The other major, so this repeats, repeats down the periodic table. So the same jump or the same exception occurs when you go from magnesium to aluminum, or when you go from calcium to gallium, so on and so forth. We would expect that magnesium would have a higher we would expect that aluminum would have a higher ionization energy than magnesium because aluminum is further right on the periodic table, so it has a higher effective nuclear charge. So we would imagine that it would hold on to its electrons a little bit more tightly. And it does, except that aluminum, you're pulling it out of a 3p orbital as opposed to a 3s orbital for magnesium. So that trend repeats for magnesium and aluminum. The other exception happens in between columns, actually I don't have the column numbers, remember, between columns 15 and 16 on the periodic table, as you go between nitrogen and oxygen. Nitrogen, again, okay, oxygen's further right in the periodic table, so we would expect it to have a higher ionization energy, but it's actually the other way around. Nitrogen's ionization energy is actually larger than the ionization energy of oxygen. The trend flips itself. So how do we explain that? By looking at their orbital structure. Again, looking at their electron configuration. So nitrogen's electron configuration is 1s2, 2s2, 2p3. Oxygen's electron configuration is 1s2, 2s2, 2p4. So that by itself doesn't tell us very much. To further explain or to get a better explanation, you need to not just look at their electron configurations, but their orbital diagrams. So nitrogen's orbital diagram, it has 2p3, so its 3p orbitals, or rather its 2p orbitals, are all half filled. Oxygen's 2p orbitals, two of them are half filled, and one of them is completely filled. So when I pull an electron off of nitrogen, I'm going to pull it out of one of the 2p orbitals, or I could pull it out of this p orbital. I mean, they're essentially the same. They're all degenerate. They have the same energy, so I can pull an electron out of either of these. For oxygen, if I pull an electron out, I'm going to pull it out of this orbital, because that one has the excess electron in it. And that electron is in the same orbital as another electron. Those electrons are sort of crammed together into the same orbital. And electrons have the same charge. They don't like being near each other. So that makes that orbital relatively high in energy. So its energy gets shifted up a little bit, simply because it has more electron-electron repulsion. So that makes it somewhat unstable. So it's a little bit easier to pull an electron out of the 2p orbital just due to electrostatic repulsion. And that's an unfavorable interaction. So they don't really want to be in the same orbital. So one of them is actually relatively happy to be pulled off of its orbital. Okay, I think that covers all of the feedback from today. If you have further questions, I would be happy to answer them either during office hours or via email, or if not, I will see everybody on Friday for lecture. All right, everyone, have a good day.